In this podcast, we're going to talk about all things related to phase changes. So we're going to talk about the states of matter. We're also going to go over changes of state. We will walk through a heating and cooling curve. We'll also talk about heat of fusion and heat of vaporization. All right, so we're kind of going back to our third grade science. We're going to talk about the states of matter first. We know that there are three states of matter: solids, liquids, and gases. Solids have a definite volume and a definite shape. They hold their own shape. You can measure their volume. Liquids have a definite volume, but no definite shape. They take the shape of the container. Gases have no definite volume and no definite shape. So no matter what the size of your container, if you put the gas into that, it's going to take up or dissipate or disperse throughout that container. So it'll take on the volume of whatever container you have, and therefore does not maintain its shape. Let's talk about changes of state. This is nothing new to you. We use the term melting, which means we're taking something in its solid state to a liquid. Freezing is the opposite. The liquid is losing energy and turning into a solid. Vaporization, also known as evaporation, is where a liquid turns into a gas. We're absorbing energy. We're heating a liquid and turning it into its gaseous phase. The opposite of that is condensation. I always think about showers and how your hot water vapor condenses against the cold shower door, and that's where your gas is losing energy and turns from a gas to a liquid. And the final phase change, I think, is a little more difficult because we just don't see it very often, is sublimation, and that's where we go directly from a solid to a gas. I always think of dry ice. And then the opposite process, which we never talk about, is deposition, and that's where you have a gas that goes directly into the solid state. It skips the liquid state. All right, this image is all for my visual learners. All right, so I want you to think of heat energy being taken from the environment. So as we move from this side to this side, we have to absorb energy or take energy in. So think of these or this direction as being endothermic. And when we release energy to the environment, so we're moving from the gaseous stage down to the solid stage, these are exothermic. They're releasing energy. My handwriting's atrocious. I apologize. All right. So essentially what we just talked through is you have solids, liquids, and gases. To get from a solid to a liquid is melting, and a liquid to a gas is evaporation or vaporization. All of these that we just mentioned on here are going to require energy input from the environment. So they're endothermic, they take energy in. We can also just skip this middle step and we can go straight from a solid to a gas, which is what we see in dry ice. It goes straight from that solid dry ice into carbon dioxide gas. Now the opposite is true. Condensation is going from a gas, I'm going to draw this because we're going in this direction, to a liquid. And you're going to have to lose energy for that because your particles need to slow down. Freezing would be a liquid to a solid. Again, you're losing even more energy from this reaction. Your energy is leaving, or heat is leaving. And again, we can also skip that liquid stage and go straight from a gas to a solid in a deposition. So one of my favorite applications of phase changes is with dehydrated foods that you would take backpacking or any freeze-dried food. Really, you don't have to go backpacking. You could just sit on your couch and eat it too. So freeze-drying actually removes water from food, and it does it through the process of sublimation. So these products essentially have a shelf life of forever, because when you remove the water, you're also taking away any probability or possibility that bacteria can grow on your food. So because they're completely dried out, there's not going to be any bacteria growing. And so these are the ones, this is the packets that I would have these freeze-dried food in the event of a zombie apocalypse, because they will last indefinitely. Canned food, no, it's got a shelf life. Freeze-dried food's where it's at. So on the next slide, we're going to show a heating curve, and on this slide, we're just going to talk about it. So if it doesn't make quite enough sense right now, just hang on until we get to the next slide. So we're going to talk about heating and cooling curves. So we're going to talk about both the addition of energy, which is what you see in a heating curve, and the removal of energy or the cooling of a substance in a cooling curve. A heating curve is going to show a solid melting or increasing in temperature to become a liquid, and a liquid becoming a gas. We're adding heat. Always put temperature on your vertical axis and the heat added on your horizontal axis. You will see plateaus on the graph. Keep in mind, these flat plateaus are actually phase changes. So the energy that's being added is not being added to increase the temperature of the substance. In fact, that plateau shows the energy, instead of increasing the temperature, the energy is going to overcome the intermolecular forces between molecules. It's increasing the motion of the molecules, so now they're starting to overcome the forces that keep them together as a solid or a liquid. This is not increasing the temperature. All right, so as promised, we are going to take a look at this particular graph. We have temperature, and I like to use degrees Celsius, although, good God, I think this is probably in Kelvin looking at those numbers. Who does that? It's good visual. We'll work with it. So we have, at this point, a solid, and ice cubes. You have a solid. Right now, as we see this temperature increasing and we're adding heat over time, as we see this line increase, okay, the temperature is increasing. Any energy is going towards raising the temperature of that water. When you see these plateaus represent the energy. Instead of going to increase the temperature, the energy is going to the motion, to the phase change. So it's these plateaus that show us our solid is beginning to turn into a liquid. We're overcoming those intermolecular forces that hold those molecules together in the solid, and they're starting to move more. At the end of our plateau, we start to see our line goes up again. Now we are increasing temperature again. So the energy being added is going to increase temperature. At this point, at this little dot that we drew, all of your substance is now liquid. So this entire red line is going to show all liquid state. And you won't see a temperature increase until all of your solid is gone and you're in the liquid state again. And then we see another plateau. This plateau represents energy being put in to move those molecules faster so that they can overcome their intermolecular forces between the molecules. So the energy is not going to increase the temperature, it's going for those molecules to overcome their forces. This is where we have our second phase change. Now we're moving from a liquid to a gas state. Okay, it's starting to vaporize. And finally, right at this point, it's all gas, just like we had all liquid at the last point, gas with 2 S's. I probably need to go home. It's been a day. You will see an increase in temperature again. That increase in temperature tells us it's all gas at this point. So something else I would like you to look at is the labels that are on here that we haven't had a chance to talk about. But this solid to liquid we call the heat of fusion. We're going to talk about that equation and what that means. This is the energy to change the state, to change from a solid to a liquid. And then the heat of vaporization. We're going to talk about that in a little bit. That's the energy it takes to convert liquid to gas. When we did our equations on our last podcast, we talked about what does a change in temperature look like? Not a change in state, but a change in temperature. Each of these red lines could be calculated. How much energy does it take to increase the temperature from here to here? How much energy does it take to increase the temperature from here to here? How much energy, again, does it take for these temperature increases? What we're going to learn about soon is how much energy, can we calculate how much energy it takes to change the state without changing the temperature. In a cooling curve, we're essentially doing the same thing, except for this time, instead of adding energy, we are losing energy. We're showing a substance that's cooling and condensing, the heat is being removed. Again, temperature on the vertical axis, heat on the horizontal. Sometimes we'll put time on there because that shows kind of a good progression over time, what happens to temperature, and we can assume or extrapolate that heat is being added or decreased. All right, so this is a cooling curve, same thing, but in reverse. I'm not going to go into the same detail I did with the other, but you essentially get the same thing. We have temperature and we have energy being removed. So right here we see a change in temperature. Okay, so this could be we could calculate how much energy is lost to the environment as this gas cools. So this is all gas at this point. Now that we see another plateau, we know that we have a change of state. So this is a gas to liquid or a condensation. Okay, there is no change in temperature. Those molecules are starting to slow down and those intermolecular forces are coming back into play. At this point right here, it is all liquid. And then we can measure how much energy is lost to the environment. This would be another Q equals MC delta T problem. When we start to plateau again, we are plateauing because we have a phase change. So now we're going from a liquid to a solid, or we're going through the process of freezing. And finally, at this last little bit, we know that we have all solid and we can further decrease the temperature of the solid. So we can also calculate again how much energy is being lost by this substance. Something that is not mentioned on here is to go from a gas to a liquid. That will be your heat of vaporization, because that deals with your anything in the gas to liquid phase, condensation or evaporation. And then down here we have our heat of fusion. We're going to learn what those are, but we can calculate how much energy is lost to convert substances from one state to another. All right, so heat of fusion, as we mentioned, is going to be the amount of energy needed to melt or freeze 1 gram of substance. I would like you to please, please, please hone in on these two terms, melt or freeze. Those are your vocab words. Anytime you see the word melt, anytime you see the word freeze, you automatically know you're doing a heat of fusion calculation. That is your code word that you're going to have that equation included. And that'll be the amount of energy needed to melt or freeze 1 gram of substance. So it's kind of a standard. If we melt, okay, we have to add energy in, that is endothermic. If we were to freeze, that would be energy leaving the substance. Energy is out, it's exothermic. Your energy that is released by melting a substance is equal to the energy absorbed to freeze the substance. Same amount of energy in or out. All right, so here's where it gets just a little bit confusing, but hopefully we can head this off. We'll be using the heat of fusion value for water unless otherwise stated, and I will give you that value. Your lab manual uses 80 with a decimal calorie per gram for the heat of fusion value. I like this value best. It's simple. Your book likes to use 79.7 calories per gram. So when you're doing your homework, you're going to have to use this number. You will most frequently see me use 80 though. It's easier to remember. So the equation for the heat of fusion is Q. Remember that Q stands for our calories. We're going to figure out how many calories are in something, how much energy is associated with it. That is equal to the mass times this value, this constant, this heat of fusion value. I would like you on not only for heat of fusion, but also this is heat of vaporization, to treat these numbers as measured numbers or inexact numbers. We came across them through measurements. Okay, there is some level of uncertainty. So when you calculate these numbers, you're going to need to apply these numbers and include these numbers in your sig fig rules. All right, heat of vaporization, or HV, is the amount of energy needed to vaporize or condense 1 gram of a substance. And again, just like with heat of fusion, you have these two keywords. Anytime a problem says vaporize or condense, that's a change of state. We're going to use a heat of vaporization calculation for this. So water has a really high heat of fusion and a high heat of vaporization, meaning it can absorb a lot of heat or energy before it is converted to a gas. So because of this, jumping back a second, because it can absorb a lot of energy before being converted to a gas, your body uses evaporative cooling. So you sweat. That liquid sweat on your body can absorb a bunch of heat from your body before it gets converted to a gas. So you get this cooling sensation from your sweat. Now, unless otherwise noted in your problem, we are going to assume we're working with water. And I would like you to memorize, just like I'd like you to memorize the heat of fusion, memorize your heat of vaporization value. It is 540 with a decimal, so 3 sig figs calories per gram. You need this value in order to do any problems that ask or refer to a vaporization or a condensation of something. The equation is Q, again this is calories, times the mass of your substance times the heat of vaporization for your substance. And again, we're mostly dealing with water here just to keep it simple. And as a friendly reminder, I'm going to say it a million times, treat your heat of fusion and your heat of vaporization as measured numbers or inexact numbers. So you're going to have to include them in figuring out how many sig figs your answer should have. We're not going to go over sample problems on this. We're going to save that for class so that we can address all the different ways you may see these.